Question number 1. The given for this problem is the pressure from steps 2 to 3, 80 bar, from steps 3 to 4, 0.1 bar, from steps 4 to 1, 0.1 bar, and from step 1 to 2, 80 bar. And the temperature for step 2 is 600 degrees Celsius. The efficiency of turbine is 0.9 and the efficiency of pump is 0.8. Required is the specific work and the thermal efficiency. The isentropic work of the turbine can be calculated by H3 minus H2. And from the steam table, we can get the enthalpy and entropy values at 800 kilopascals and 600 degrees Celsius. And we can also get the saturated liquid and saturated vapor values of entropy, enthalpy, and volume at 10 kilopascals. And since the step 2 to 3 is an isentropic process, we can consider that S2 is equals to S3. And to solve for H3, the mass fraction X3 is needed. And we can solve it by S3 is equals to the saturated liquid value of S3 plus X3 multiplied to the quantity of the saturated vapor and saturated liquid values of S3. And by plugging in our values, X3 is equals to 0.8491. Now that we have the value of X3, H3 can be calculated by H3 saturated liquid plus X3 multiplied to the quantity of saturated vapor minus saturated liquid values of H3. Thus, H3 is equals to 2223.7 kilojoules kilogram Kelvin. And we can now get the isentropic work of turbine by subtracting our values of H3 minus H2, which is negative 1415.8 kilojoules per kilogram. Then, the efficiency of turbine is 0.9, and to get the turbine work, we will multiply the efficiency by the isentropic work of turbine. And to solve, turbine work is negative 1274.22 kilojoules per kilogram. And the new value of the H3 at 0.9 efficiency is 2365.28 kilojoules per kilogram. And Q condenser can be calculated by H4 minus H3. And plugging in our values, the Q condenser is negative 2173.45 kilojoules per kilogram. Isentropic pump work is calculated by volume multiplied by P2 minus P1. And plugging in our values, converting kilopascal centimeters cubed into kilojoules, the isentropic pump work is 8.07 kilojoules per kilogram. The given pump efficiency is 0.8, and to calculate for pump work, isentropic pump work is divided by the pump efficiency. Thus, pump work is 10.09 kilojoules per kilogram. H1 can be calculated by H4 plus the pump work at 0.8 efficiency. H1 is equals to 201.92 kilojoules per kilogram. Q boiler can be solved by H2 minus H1. Plugging in our values, the Q boiler is 3437.58 kilojoules per kilogram. Next, net work can be calculated by adding turbine work plus pump work. The net work is negative 1264.13 kilojoules per kilogram. Alternatively, by adding the negative values of Q boiler and Q condenser, the net work is negative 1264.07 kilojoules per kilogram. The efficiency of the cycle is calculated by dividing the absolute value of net work by the Q boiler. Thus, the thermal efficiency is 36.77%. Question number 2. The given for this problem is an isobutane heated at 3400 kilopascals to a temperature of 140 degrees Celsius and an expansion in the turbine with a turbine efficiency of 0.8, which produces a superheated vapor at 450 kilopascals. The pump efficiency is 0.8. The basis is 1 mole isobutane with a mass flow rate of 75 kilograms per second. Required is the work net and the thermal efficiency of the cycle. The constants for isobutane can be obtained from table C.1, and by using this formula with delta S is equals to 0, by using our user-defined function, T2 is equals to 359.35 Kelvin. Turbine efficiency is solved by delta H divided by the isentropic delta H. Thus rearranging it, delta H is equals to turbine efficiency times the isentropic delta H. Delta H from step 1 to 2 is equals to the turbine efficiency times the delta H isentropic, which can be solved by using the UDF. 0.8 times negative 6491.73 is equals to the delta H12, or our work turbine is equals to negative 5193.38 joules per mole, and the new T2 at 0.8 turbine efficiency is 370.58 Kelvin. Steps 2 to 3 is an isobaric process, which means P2 is equals to P3 is equals to 450 kilopascals. And to solve for T3, the Antoine equation is used. And given are the constants for isobutane for the Antoine equation. By rearranging the equation to solve for T3 and plugging in our values, T3 is equals to 307.04 Kelvin. The Q condenser, or our delta H23, is calculated by the delta H superheated to saturated vapor minus the delta H vapor. The delta H superheated minus saturated vapor is solved by using our user-defined function, which is negative 6,935.11 joules per mole. The normal heat of vaporization is needed first to solve for the delta H vap. The normal heat of vaporization can be solved by using the Radell's equation. And by plugging in our values, the normal heat of vaporization is 21,143.95 joules per mole. And to solve for the delta H vap, we will use the Watson's equation. And thus, again, by plugging in our values, the calculated delta H vap is 18,344.96 joules per mole. We can now solve for the Q condenser, or our delta H23. The solved value is negative 25,279.96 joules per mole. Steps 4 to 1 is an isobaric process, which means P4 is equals to P1 is equals to 3,400 kilopascals. The isentropic work of pump can be calculated by volume multiplied by P4 minus P3. For saturated liquids, the saturated volume is obtained by Vc multiplied by Zc to the power of 1 minus the reduced temperature to the power of 2 over 7. Plugging in our values, the saturated vapor is 112.33 centimeters cubed per mole. By using the obtained value of saturated vapor, we will plug into the isentropic work formula and convert the kilopascal cm cube into joules. The isentropic work of pump is 353.84 joules per mole. Pump work is obtained by isentropic pump work divided by pump efficiency. 353.84 joules per mole divided by 0.8, which is 442.30 joules per mole. And to obtain the molar flow rate, the mass flow rate is converted into grams divided by the molar mass. The molar flow rate is 1290.37 moles per second. The net work can be calculated by multiplying the molar flow rate to the net work, which is the turbine work plus pump work. The solved net work is negative 6,132.22 kilowatts. Efficiency can be calculated by the absolute value of net work divided by Q boiler. The net work is the addition of the negative values of Q boiler and Q condenser. Thus, by rearranging, Q boiler can be obtained by adding the negative values of the net work and the Q condenser. And by plugging in our values, dissolved thermal efficiency is 15.28%.
For problem number 3, we are given a gas turbine unit receives air at 1 bar and 300 Kelvin and compresses it adiabatically to 6.2 bar. The compressor efficiency is 88%. The fuel has a heating value of 44,186 kilojoules per kilogram and the fuel to air ratio is 0.017 kilojoules per kilogram of air and the turbine internal efficiency is 90%. The given is summarized as follows, where F stands for fuel, T stands for turbine, C stands for compressor, and A stands for air. What is required is the work done by the turbine, work done to the compressor, and the thermal efficiency. So next is, we have the following diagram showing PV diagram of the gas turbine and the temperature entropy diagram of the gas turbine respectively. Here we have A to B and C to D to be adiabatic and B to C and D to A to be isobaric. So shown below is an example of a gas turbine. So we will use states A, B, C, and D in solving our equation later on, and we will use B prime to be isentropic to A and D prime to be isentropic to C. So for our solution, we start with process A to B, which is adiabatic compression, where when given T and P, the polytropic equation becomes this form. Substituting the values for TA, PB, PA, and the gamma, we will have the value for TB to be 473.23 Kelvin. To get TB prime, we use the thermal efficiency or the efficiency for the compressor. So we use this form, which is the heat supplied over the work done. So substituting the values, we get the value for TB prime to be 496.85 Kelvin. Next, to get TC, we use the process B to C, in which it is the heat supplied in the cyclic process. So we use the general form MCP is equal to the heat supplied, which is MFQF. And we use the mass to be the total mass, which is the sum of the masses of air and fuel. So we multiply the form or the equation by 1 over MA to use so that we could use the value for mass of fuel over mass of air, or the ratio of their masses, which is 0.017. So now our equation becomes this form. Substituting the values, we get the values for TC to be 1140.80 Kelvin. Next, we use the process C to D, which is adiabatic expansion. We use the same polytropic equation from steps A to B, and substituting the values, we get the value for TD to be 723.20 Kelvin. Next, to get TD prime, we use the efficiency of the turbine, which is the work done by the turbine over the heat supplied to the turbine, or the energy supplied to the turbine, which is equal to its enthalpy. So TD and TC, so we have this form, which is TD prime minus TC over TD minus TC. Substituting the values for TC and TD and the efficiency of the turbine, we get TD prime, which is shown in our graph, to be 764.96 Kelvin. Next, we could obtain now the compression work done by the compressor, or done to the compressor, by using the polytropic work equation shown below, where R for air, or the ideal gas constant for air, is equal to 0.287 kilojoules per kilogram. Substituting the values, we get the value for the compression work to be negative 169.66 kilojoules per kilogram. Next, we get the expansion work done by the turbine by using the same polytropic work equation. Substituting the values, we get the expansion work by the turbine to be 323.92 kilojoules per kilogram. For thermal efficiency, we use the equation work net, or the net work, divided by the heat supplied, in which the net work is just equal to the absolute value of the work done by the turbine minus the absolute value of the compression work. Substituting the values, we get the value for the net work to be 154.26 kilojoules per kilogram. Next, we are already given with the heat supplied. However, we will convert this to per kilogram of air by using our ratio. We get the value for the heat supplied to be 751.162 kilojoules per kilogram of air. Substituting the values of the heat supplied and the net work, we get the thermal efficiency to be 20.5%.
For problem number 4, we are given with a diesel engine wherein volume ratios of compression and expansion are 15.3 and 7.5 respectively. The pressure and temperature at the beginning of the compression are 1 bar and 27 degrees Celsius. We are asked to determine the cycle efficiency when ideal engine is assumed. Fuel consumption per kilowatt-hour is also asked given the indicated thermal efficiency, mechanical efficiency, and calorific value. To calculate for the efficiency of the cycle, we use equation 8.7, which is given by 1 minus 1 over gamma multiplied to 1 over volume ratio of expansion raised to gamma minus 1 over volume ratio of compression raised to gamma all over 1 over volume ratio of expansion minus 1 over volume ratio of compression. Substituting the given values, we get 0.6048419869 or 60.48% cycle efficiency. Moving on, since for 1 kilowatt-hour of energy produced, we have total engine efficiency multiplied to mass of fuel, calorific value of oil, and the conversion of 1 kilowatt-hour per 3,600 kilojoules. To get the thermal efficiency, we multiply 0.5 to the cycle efficiency. We now have 0.3024209936 thermal efficiency. After that, total engine efficiency is given by mechanical efficiency multiplied to the thermal efficiency, to which we get 0.2419367948 total engine efficiency. Going back to our equation, we substitute calculated values to get 0.354283796 mass of fuel consumption, and since we are asked to determine fuel consumption per kilowatt-hour, we have 0.354283796 kilograms per kilowatt-hour fuel consumption.